Hi everyone, welcome to this geometry tutorial video. Today we'll be looking at special right triangles. So we'll be in chapter 5, section 8 of your textbook. So please open your textbook to that section and follow along. Remember to take notes and examples down as you watch this video. So normally, to find the length of all the sides of a right triangle using the Pythagorean theorem, you need to know two sides of the triangle. So in this case, two sides to find the third side, in this case, the hypotenuse. Now, special right triangles are special in the sense that you only need to know one side of the right triangle to know the other two sides. So let's take a look at what are these special right triangles. Special right triangles, there's two types. There are 45, 45, 90 right triangles. And what I mean by that is that's classified by their angle measures. It has a 45-degree angle, 45-degree angle, and a 90-degree angle, making it a right triangle, obviously. And then the second type is a 30, 60, 90 right triangle. So let's take a look at these two types of special right triangles, one type at a time. So with the 45, 45, 90 right triangle, let's start our discussion with a square. So we know that a square's sides are all congruent, and I've labeled their side lengths x, all of them x. And we know that each of the interior angles of a square are 90 degrees. So what I'm going to do is I'm going to go ahead and draw a diagonal from one angle to the angle opposite it, and that dashed line is going to bisect the two angles I've drawn it from. And what it's going to do is split the square into two isosceles right triangles. And what I've done is drawn one of these two triangles that it forms over here. And so we have half of the square, with the hypotenuse being the dashed line that I just drew. Okay, and so you can see that the two legs of the right triangle are still x. That was still the two sides of the square. Okay, so this is an isosceles triangle, an isosceles right triangle. And since the dashed line bisected the two right angles, we have these two angles right here are 45 degrees each, so 45 degree angles each. Okay, so we have our 45, 45, 90 triangle, right triangle, excuse me. So we have the two sides in terms of x. What I want us to figure out is, can we express the length of the hypotenuse in terms of x as well? So let's figure that out. Okay, so we still have our 45, 45, 90 triangle. I've redrawn it here, and I have the Pythagorean theorem right here. So let's go ahead and plug in the two x's for a and b and see if we can derive an expression for the hypotenuse in terms of x. And you'll see what I mean in just a second. So a is going to be x. So a squared is x squared, plus b is also x squared, equals c squared. And what we're trying to find is an expression for c in terms of x. So we have x squared plus x squared equals c squared. Okay, well, we have 2x squared, so we can combine those like terms. So we have 2x squared equals c squared. Okay, so we want to just solve for c. So we're going to take the square root of both sides. And since we have x squared under the radical, we can remove that from the radical, so we just have x. But the 2 has to stay underneath the radical. So c equals x times the square root of 2. So we found the length of the hypotenuse in terms of x. And what I've drawn here, right over here, is a little chart. And I've labeled each of the sides of the right triangle, A, B, and C. And let's go ahead and fill in the second row here, all the side lengths we know in terms of x. We know that A is x, B is x, and C, the hypotenuse, is x square root of 2. Great, so we have all the side lengths in terms of x. So if we know what x is, we can solve for any of the other two sides. So let's do an example seeing how we can do this. Okay, so now let's say that x equals 5. If we fill out our chart again, and for a 45, 45, 90, it'll always look like this. If we know what x is, we can easily solve for the other two sides. So let's just say that we know that a is 5 because it's x. Well, b is also 5, obviously. And then c is 5 square root of 2. Now that was really simple. And again, it just comes back to the Pythagorean theorem, but the reason why this was so simple is because we have a 45, 45, 90 special right triangle. Okay, let's do one more example. In this case, we know the hypotenuse. We know C is 12. So let's fill out this table again. We know this is x, x, x square root of 2. All the sides are in terms of x. If we know one side, we can solve for the other through two sides. So in this case, we know C is 12, or x squared of 2 is 12. So what we need to do is solve for x. What are the lengths of the other two sides? We know that this is 12. So what are these two sides? Okay, let's solve for x. Well, we're going to divide by the square root of 2 on both sides. And on the left-hand side, square root of 2 cancels out. So we're left with x equals 12 over the square root of 2. Okay, so now we have to rationalize our denominator. So we're going to, like we already know how to do, we're going to multiply by 2, square root of 2 over square root of 2. And what we're going to get is 12 square root of 2 over 2, which is going to be equal to 6 square root of 2. So each of the legs are equal to 6 square root of 2. Okay, very good. Now, let's look at the 30, 60, 90 special right triangle. So to begin our discussion with this, let's look at an equilateral triangle. Remember, an equilateral triangle has all sides congruent and all angles congruent, all the angles being 60 degrees. And for each of the sides of the equilateral triangle, I'm going to say that the side lengths are 2x, and that'll become clear while we're doing that in a second. So what I'm going to do is draw an altitude from this angle right here, right down to the base, and the altitude obviously makes a 90-degree angle with the base. And if I were to chop this equilateral in half right down the altitude, I would get two right triangles. Okay, and I've drawn one of these right triangles right here. So let's see what kind of a right triangle it makes. This altitude has split the 60-degree angle right here in half, so I now have a 30-degree angle. The angle right here at the base is still 60, and the altitude made a 90-degree angle, so I have a 30, 60, 90 right triangle. Okay, so let's look at the side lengths now. Since the altitude split the base in half with the equilateral triangle, the base of my new triangle, my 30, 60, 90, is only half of that, or x. The hypotenuse is still 2x. And then this longer leg across from the 60-degree angle, I want us to see again if we can find the side length in terms of x. So let's turn our attention to doing that right now. So I've redrawn the 30, 60, 90 triangle here with side length x across from the 30-degree angle and 2x as the hypotenuse. And what we want to do is solve for this second leg, the long leg, in terms of x. So let's use the Pythagorean theorem to do that. So we have a squared plus b squared equals c squared. Let's plug in what we know. I'm going to say that the short leg is a. So I'm going to plug in x for a. We don't know what b is, the longer leg, so we're going to solve for b. And we know c, the hypotenuse, is 2x. So I'm just plugging these values in to the Pythagorean theorem. Okay, so we get x squared plus b squared equals 4x squared. Now I'm going to solve for b, so I'm going to subtract x squared on both sides. And b squared is going to be equal to 3x squared. Okay, now we'll take the square root of both sides to just get b. b equals x times the square root of 3. Okay, so now we have all three sides in terms of x. Let's go ahead and write that in our chart right here. A, or the short leg, we'll say is just x. B, the longer leg, is x square root of 3. And again, A is across from the 30, B is across from the 60-degree angle, and C, across from the 90, is 2x. Okay, so let's do an example where we need to find two side lengths when we're given one side length. So in this case, we know that x equals 4. So let's go ahead and plug in fill out our chart in terms of x. This is an x, 2x. Okay, so we know that x equals 4. All right, so a is 4. B is just 4 times the square root of 3. And then c is just going to be 8, or 2 times 4. Well, that was easy. Again, this is just derived from the Pythagorean theorem, but it's so easy because it's a special right triangle, 30, 60, 90. Let's do one more example. In this case, I know what the longer leg is. I know what B is. And I want to solve for the shorter leg A and the hypotenuse C. So let's fill out our table. Square root of 3 and 2x. Okay, in this case, we know that 15 across from the 60 is B, or x squared of 3 equals 15. So in this case, we need to solve for x so we can solve for A and for C, these other two side lengths. We know this is 15 already. Okay, so let's solve for x. Let's divide. Let's by square root of 3. That crosses out, cancels. But we need to rationalize the denominator in this case to solve for x. So we're going to multiply by square root of 3 over square root of 3. And we're going to get 15 square root of 3 over 3, which equals 5 square root of 3. Okay, so x equals 5 square root of 3. And 2x is just going to be 10 square root of 3, or 5 times 2 times the square root of 3, 10 square root of 3. Okay, great, guys. So in review, we've learned how to solve for two side lengths of both the 45, 45, 90 and 30, 60, 90 special right triangles when we're given one side length. Now this concept is going to be really important in trigonometry and in pre-calculus. So if you have any questions, make sure to write them down and we'll discuss them in class. Great job, everyone.